Okay, so we're recording now. So here's the deal with Squeeze Theorem, and I found this really great resource last night. So think of the Squeeze Theorem as a sandwich. So they call it like the sandwich theorem. And let me go back to the notes also, because I think that might be a good place so you can make any annotations to your notes. Give me one sec here. So if you have your 2.2 notes out, you can make some updates to it or changes if the way I explain it is a little different. So some people call it the sandwich theorem. Now, let's say we have a different graph. We'll do a graph that's a little different than this one. Let's say I have like y equals x squared times sine 1 over x. Let me turn these off. Okay. Here you have y equals x squared times sine 1 over x. Okay. Think of this it's going to be kind of corny. Think of this as a hamburger meat. Or like if you like In-N-Out, I know some of you guys talked about In-N-Out on the first day. You know, hamburger meat, maybe other ingredients. You know, maybe there's like cheese or sauce, or I like pickles. I'm not a big fan of mayonnaise. Some people like mayonnaise, ketchup, onions. My wife doesn't like that, but so think of that as a hamburger. That's the middle. Okay. These right here are the buns. This is the bottom bun. Because if you think about a hamburger bun, you know, it's both sides are not the same, right? One looks a little more flat, one looks a little more concave around. This is the top bun. If you are making like a peanut butter and jelly sandwich, yeah, both sides of the bread look the same. But I think for the sake of like this argument here, you got the bottom bun, you got the top bun. You don't really flip it over. That's kind of weird. No one makes a hamburger that way and eats it that way. That's strange. So anyway, you have the bottom bun and the top bun. So here's the middle. This is the graph, and that's what we're interested in. We're interested in finding that limit. We'll say as x approaches 0 of x squared times sine 1 over x. Now, here is the issue. Analytical techniques don't work. I can't think of an analytical technique to find this limit. So what we're going to do is we'll look at graphically. Like if I trace on this, you know, so let's say I start here. You know, sometimes the y value goes up, sometimes it goes down, and then the up and down motion becomes a little bit less pronounced, I guess, or y is getting closer and closer to 0. Now I can't plug in 0 spot up or straight up. Yeah, it won't let me because maybe if I zoom in. Yeah, see it says undefined. Yeah, which should make sense because the sine of 1 over 0, well, 1 over 0 is undefined. How do I find a sine of that, right? And it's weird because you're also multiplying by 0, but then you're doing sine over, it's just such a strange phenomenon. But the bottom line is that graphically, it does get close to 0. Or if I, and actually I'm really excited for this, I did finally get around to downloading the TI emulator. TI Smart Food, there we go. Let's just take a moment. The other thing I'm going to do too is there's a more complicated procedure. I'm going to try to actually get my actual calculator superimposed on the screen. There's a thing called a different kind of, there's a different kind of emulator that you have to do, but it's a little bit like brain surgery to a rocket science to figure it out. So I'll get that figured out. I tried doing it yesterday and it was being challenging. But if I go to y equals, if I do x squared, oh, doesn't like that, x. Okay, well, hopefully that works. X squared times, oh goodness. Okay, well, this will be a little choppy. X squared times parentheses, let's just use my keyboard, sine of 1 over x, enter. Make sure my mode is radians, which it is. And of course, if I graph it, it's gonna look kind of weird, but that's okay. But if I go out to the home screen and do alpha trace y1 and type in something close to 0, like that, you see it says 8.26 in scientific notation times 10 to the negative 7 power. Or if I repeat that and insert a negative, I get that also. So sometimes we just have to resort to numerical or graphical techniques to get the answer. But is there an analytical, is there a way I can actually still figure this out without doing it graphically or numerically? So, and actually, let me take this back. Typical analytical strategies, because what we are going to do ultimately is going to be analytical with the squeeze theorem. But typical analytical strategies like factoring or other stuff may not work. We have a question here. How do you choose the bread? Okay, the bread. Great question. Yes. Do you go rye? Do you go wheat? Well, no, I was just kidding. Hey, how do you choose the bread? Okay, so fantastic question. What you do is look at the part that's not undefined. So what part of my sandwich is not undefined? This right here, the x squared. So what you first do, let me clear the screen. What you first do is you make this the meat. The part that made it undefined. The part that was an issue. That was the issue, right? And what you do is you try to find the range. So what I could do is I could deliberately delete this. Whoa, that's crazy. Okay, you guys see the range here. What's the lowest point? What's the highest point? -1 to 1. So in order to find the meat, so this is where you should be annotating your notes. In order to figure out what f of x is, choose the part of the function that is creating an undefined issue. And what would that be? Obviously the sine 1 over x, because you need 1 over x. Yes, I would. Yes. The question is, do you always need a graph to determine the range, or should we know how to do it without? No, just graph it. That's fine. I'm letting you guys use graphing calculators for your assessments. That's fine. Just graph it. But we should be aware that sine, excuse me, has a limited range. So going back to Desmos again. So that will be our meet, sine 1 over x, and it was between -1 and 1. Now, we didn't truly have sine 1 over x. Think of sine 1 over x as just meat. Maybe it's a burger that way. Maybe you do. I'm sorry if you do. We want to upgrade, right? And the thing of -1 and 1 is like, your typical white buns from you get from the store, right? I want an upgrade. I want maybe like some nice cheese with it, or some fresh lettuce. And I don't want typical bread. I want like a brioche bun or something. My son loves brioche bread. So I want like an upgrade. So what do we do for the upgrade? X squared. Think of x squared as the upgrade. You know, when you go in and out, they say, oh, do you want like animal style? Think of it that way. I don't know if that makes sense, but think of this as the upgrade. So I'm going to multiply this by x squared, multiply this by x squared, and multiply that by x squared. But first off, is this a true statement? Yes, it is. And what happens is that the just meet part is f of x. And then the lower bun we can call g of x according to our notes. And the upper bun, or the top bun, we call it h of x according to our notes. Oh, sorry. Hold on. This is just being stupid. Yeah. And so think of the x squared as like an upgrade. So we have another question. Yes, the range always becomes the buns, 100%. Yes, the range always becomes the buns. And so think of this as -1 as g of x and 1 as h of x. Now, first off, what's the limit? Well, actually, we won't worry about that just yet. So we'll do the upgrade now. The upgrade is x squared. So now you got negative x squared is less than or equal to x squared times sine 1 over x less than or equal to x squared. This is still a true statement because we know this was true graphically. -1 is less than or equal to sine 1 over x, which is less than or equal to 1. And by multiplying x squared, fine. So now I get the expression I really want to work with. This right here. This is what the squeeze theorem is saying. The squeeze theorem is saying is that if this is true, if this statement is true, which it is, and if the limit as x approaches 0 of negative x squared equals the limit as x approaches 0 of x squared. So basically, if these two limits equal each other, the lower bun limit and the upper bun limit, or the bottom bun and the top bun, if both those limits are equal to the same thing, and actually they do. Don't buns come from the same thing, right? They come from a loaf of bread, right? You just slice it. So they are the same material, same ingredients. Then, so if you have two conditions, if this is true and if this is true, then the limit of x approaches 0 of the meat, of the stuff inside, is also going to equal 0. It's also going to equal the same thing. And if this is true and equals L, some number, whatever number that is, then the limit of what's inside will also equal the same thing. And I'm going to show you a graphical demonstration just a bit to really close the loop here. We got some questions. So the flipping inequality, let me come back to it in a second. Someone asked about the flipping the inequality part. For now, we're not going to worry about that because I want to keep it simple. Yeah, go over. Yeah, I'll explain being careful with the algebra. Nico asked, can you always use this method as x approaches 0? No, you can do it for any, x could be approaching anything for the squeeze theorem. We do it for 0 for simplification, but it could be anything. Can we look at an example? Sure. Let me think of that one. Thank you, Catherine, for bringing that one. The buns don't equal 0. Great questions. And would this require us to be able to immediately identify the limits of graph x squared or more complicated ones? I think we'll keep it pretty simple for the squeeze theorem. I think for x squared, because it's polynomial, we know it's 0. I'm going to keep it pretty straightforward, just so you know. I just want to make sure you guys know the squeeze theorem. I'm not going to make it too complicated. So great questions, though. Hopefully I tackle them. So let me clear a screen. Let me turn these on.
I have a question.
Hey, good.
On the example, like from the notes, example 18, when we had sine x between -1 and 1, did we know that like more just from analytically, like that sine x is always going to result in a number between
sine function is always limited in its range.
Okay, so like,
always, yeah.
that from like a graph, just more because we know about the way.
Just because well, actually, let's think about just going basic SOHCAHTOA, right? Beta, opposite hypotenuse. So the definition of sine is sine of an angle equals opposite of hypotenuse. Well, here's the deal. The opposite can never be bigger than the hypotenuse, right?
Yeah, okay.
So that's why. Now, I just graphed x squared and negative x squared. This is the top bun. This is the bottom bun. This is the meat. It's red. If you're like me, I like it more medium rare. So anyway, trying to make fun of this. So as you get closer, notice how the red curve is sandwiched in between the blue and green curves. That's why we call it the squeeze theorem. The graph is squeezed in between the top and bottom functions. And they're pretty similar in some ways. You have x squared, but what we did initially we did this without the buns. We saw this was happening. Or sorry, without x squared, negative x squared. So we had like more, I guess, simple buns, -1 and 1. And then we did an upgrade. But we see that it's sandwiched in between the two. And we know that these two limits, x squared, negative x squared, is 0 when x approaches 0. So naturally, this will also approach 0 when you see it graphically here like this. So whenever you have a function that's in between two functions, and you have the limits for both top and bottom functions, the middle is going to have the same limit. Think of it that way. So let me write that out. When you have, maybe I'll type that up. That might be easier. And I'll get to the question in chat in just a second. It's taking a sweet little time. Oh, why is it doing that? Let's increase the font here. When you have a top function and a bottom limit x approaches That's essentially what's happening. We have a top function and a bottom function. They both share the same limit as x approaches particular. So they both shared a limit of 0 as x approaches 0. X approaching a particular number, which was 0 also. Then any function that's in between those two functions, for all x values, is always in between it, will have the same limit. Of course, as x approaches the same number that we have for the top and bottom functions. That is a squeeze theorem in a nutshell. And probably I could even save that and put that in Schoology too. So let me do a quick save. Why are you so slow today? Come on. Okay, there's a question. How can you do squeezing without graphing knowing what the graph would look like? No, don't worry about that. I do want you to graph it. I want you to approach this from a graphical standpoint. It's just going to be easier for you. I mean, yes, once you know, like someone like me, I know how these look because I've done this for so long, sure. But in your case, totally graph it. Don't worry about that. So let's just recap other parts of the notes before we move on to other stuff. So there was some other scenarios where you know you had to like you had to flip stuff. Okay, what am I doing today? Here we go. Yeah, there are other things. There are some nuances that we just have to discuss that some of you guys brought up in the chat. Yeah, and actually some said like, what if your limits don't equal 0? Or for x approaching different numbers. Let me see if we cover that. I mean, I do want to be mindful of the time because we have other stuff we have to do. But it's good that we're having this discussion. I mean, it's not something we want to gloss over. The example 16 was just like what I just did. Instead of x, we did x4. Fine, not a big deal. Here, they simply replace x4 with x cubed. The problem with, and this is as x approaches 0. So here you have x approaching 0. The problem is that when you're approaching 0 from the left side and from the right side, x cubed could be positive or negative. So if I were to go back to Desmos and make an update, kind of hard to see. Yeah, it's kind of really challenging, but I mean, do you have x cubed, which is right above, negative x cubed, which is right below? And you kind of have that red curve that is tangent. It's just really, really hard to see. The only problem is that when you're doing those limits, when you do the left and right hand limits as x approaches 0, when you're approaching 0 from the left side, that does turn this x cubed to a negative value. So now the meat becomes negative when you're doing the left-hand limit. So when you're doing the left-hand limit, this part right here, for the most part, will have something be multiplied by a negative. So when you multiply something by a negative, because remember, we are multiplying this by x cubed, right? But when you're approaching 0 from the left side, you are changing the signs of all these, technically. That's why you reverse it. It doesn't make any difference in your answer. I mean, you still have to know that each of these limits are 0, and therefore that's 0. So it doesn't, it's kind of a minor thing. It's more trivial, to be honest with you. But to be proper, you should flip the inequalities. So I wouldn't really worry about that. Hopefully that answers your question for that one. And of course, this is the right-hand limit. We'll multiply x cubed when x is slightly bigger than 0. Sure, I'm multiplying something that's very positive anyway. It won't matter. The bottom line is find a function above and below, and anything that's causing the undefined part, the 1 over x is causing that. So you start with sine 1 over x, you find the range of it, and you multiply it by whatever you need to make it truly what you want to find. And then you, of course, find these limits individually, which was easy. You know, there's a 0 from left and right side. Therefore, this must also be 0. That is the squeeze theorem. Yeah, and someone asked, like, can we see something when these are different numbers or when it's not approaching 0? Let me think about that because I really want to get to the other stuff. Someone asked that question, like, what if you this limit's not approaching 0, it's approaching something else. Let me explore that a bit more, and I'll get back to you guys on that. But for now, let's just keep it kind of simple. Yes, you can graph it. It should be pretty straightforward. I'll probably do something just like this and just want you to kind of state it. So that's kind of all that. Okay, so we had that discussion. That's good. I'm glad. Okay, there's still homework to review. Is there anything just really burning that you really want to ask? And I'll just kind of quickly say what you needed to do for the first few problems is just graph or make a table, and just see what the limit's approaching. That's all. And this is infinity or negative infinity, so you can see the left and right ends. So hopefully that's okay. Like again, you could just do cosine 1 over x in Desmos. And just zoom out. And you see if you go forever to the left or forever to the right, it's approaching 1. That's all. When they ask to describe the end behavior, they just want you to find the limit as x approaches negative infinity and limit as x approaches positive infinity. It's not really a sign chart necessarily. The sign chart was more for the vertical asymptotes. So if someone asks, when they say describe the end behavior, is that just a sign chart? Not really. What they're asking for is the limit as x approaches negative infinity and the limit as x approaches positive infinity. That's it. Should we do 1 through 11 analytically? No. Actually, it's impossible to do those analytically. So I will be very explicit if I want you to say, hey, you got to just do a graph or table, or I want you to do this analytically. I will be very, very clear about that. The textbook sometimes lacks that clarity. That's kind of, I need to be a little more thorough and put some hints to make sure you guys are clear about that. So that's just my fault. I'll make sure I'll be more mindful about that. For number 9, find a limit, confirm your answer using the squeeze theorem. Okay, so let's use the squeeze theorem for number 9 and for number 11. And squeeze theorem can apply for even when x is approaching positive or negative infinity. So in this case, let's actually dissect this one. Number 9. I would write it like this: 1 over what do we think here? 1 over x squared times 1 minus cos x. Shoot, this is a little tricky. Give me 1 second to think about this one. Oh, this is when x is approaching infinity or negative infinity. Actually, I think we should be okay with that one. The 1 over x squared is causing, well, actually nothing's being undefined here. I suppose, just give me a second to think about this one. I guess we could break it up. That's probably what I would do. I would probably do this. That'd be probably the first thing I would do. Because I kind of already know what the first limit's going to be. I already know that's going to be 0. We've already had that discussion. This is the one that's a little weird. And cosine x, I think, is what causing things to be a bit strange. So, because cosine x kind of goes up and down a lot. Can't just graph. Oh, actually, good point, Tiffany. Yes, I'm making this more complicated than I should. Yes, thank you. Yeah, if we graph y equals, yeah, thank you, Tiffany. You just cleared up for me. You should be teaching this class, not me. So, anyway, yes, you're 100% correct. You're seeing the patterns. So let's go back to Desmos again. Let's do 1 minus cos x. Does it have a limited range? Absolutely. What is the range for that? From 0 to 2. So now in this case, where are my buns? 0 and 2. What's my meet? 1 minus cos x. What's my upgrade? 1 over x squared. And what's the limit? And so then obviously this becomes just 0, of course. That's 1 over x squared times 1 minus cosine x. And of course, it's 2 over x squared. What is the limit for each of these two far left and far right functions? Those are each going to be 0. The limit as x approaches infinity of 0 is 0. And the limit as x approaches infinity of 2 over x squared is also 0. Hence, this limit is going to be 0. So yes, what you need to do is for the meet part, it's really, you have to find, I did say it's anything that can cause it to be undefined. I said that for the previous example. Really, it's anything that could be sandwiched in between two things. It has a limited range. Does 1 minus cos x have a limited range? Absolutely it does. And graphically, we see it's between 0 and 2. So you start your sandwich that way. You do your upgrade by multiplying 1 over x squared, so you get what you truly want. And you find the limits of the left and far right functions, which are 0, limit of 0. Sorry, limit as x approaches infinity of 0 is 0. Limit of this is also going to be 0. So yeah, that's what happens there. Yeah, totally. Someone said, could you also just think about the values of cosine x like -1 to 1, and plug those values to the function to see the new boundaries? Yeah, I would do that. Yeah, then plugging the values to the function to see the new boundaries. Yeah, I think that would make sense. So anyway, and just quick go to other parts of the homework. Where is it right here? There's also this right here. I'm looking at 2733. Those are vertical asymptotes. Usually what you want to do, come on, let me clear my screen. By inspection, see what makes each of these 0 first. And then just do the left-hand limit and the right-hand limit. That's where a sign chart might help to kind of see what's happening to the y. And then sometimes you do have to kind of maybe plug in values close to it to kind of just see, okay, is it going towards infinity or negative infinity? The bottom line is that if it's not being crossed off by anything from up above, then it will be a vertical asymptote. Instead, it'll be a hole, and the hole would appear at when you take a limit as x approaches that number. Like in this case, I don't think these had any holes actually. Yeah, I don't think any of these had holes. So then, of course, other part of the homework. Yeah, I said ignore part A. Part B, just knowing the trends, looking at the degrees. That's what we do for that one. And then, of course, the last one was just kind of like a little AP quiz. You have all this stuff here. Just reviewing some old stuff. And this, it looks like this was dealing with squeeze theorem stuff here. Question. Oh, how do we know how it's a hole? Yeah, we know it's a hole. And I'll look at 30. We'll go back to 30 and 33. We know it's a hole. If you look at the notes, The notes is the best part to help you with that. These go away. We're here. Nothing goes away. So your vertical asymptotes are x equals 2 and -7 here. Here it's just going to be x equals -7. That's how you can tell. And if you were to actually take the limit of the second function here, as x approaches 2 from either left or right side, it gets closer and closer to some number. In fact, I think it gets closer to 1/5, I think. Or no, 1/9. Yeah, because it reduces 1 over x plus 7. So if I take the limit as x approaches 2 of this, so you have a hole at 2, 1/9. And if you're a graph it, you would see that for yourself also. Someone asked about 31 and 33. Let me look at those again. Yeah, okay, the trig stuff. Sorry I glossed over that. Cotangent, I think you just have to look at it graphically. I think sometimes we kind of forget how those look. You can't take the cotangent as 0. Remember, cotangent is 1 over tangent x. On the unit circle, remember that's 1, 0. Tangent of your angle is y over x on the unit circle. So you could do tangent of 0, that's fine, but then if you're doing 1 over tangent, you're doing it so it's undefined. So that's why you're gonna have vertical asymptotes at any integer multiple of pi. For 33, you could actually reduce that. Tan is sine x over cos x, divided by sine x, so you get 1 over cos x. Obviously, cosine is 0 at pi over 2 and 3 pi over 2 and so forth. So you just have to kind of generalize it and say, well, it's just going to be, it's actually the same thing as this one right here. Because secant is 1 over cosine. 32 and 33 are actually identical. They're the same function. So you have to kind of generalize it. But again, that sometimes graphing it might help. I'm fine if you do that. So I think the bottom line is we just need to know this. If x is approaching some number and you wind up getting this happening, that's a vertical asymptote. That's what I really care about, that you know that from a limit perspective. Okay. Well, I think you guys need to do some group work. So let's do some limits review. I'll just have to talk a little about 2.3 at the end, and then of course do a video on it. I think that's really the best way to handle that. But you guys definitely need to do some group work. So let me stop sharing, stop recording.